Now let's talk about circular motion problems. Remember, anytime you have an object moving in a circle, then there's a centripetal force acting on it, and there's a centrifugal acceleration always pointing to the center. So F is to the center, and the centrifugal acceleration is also to the center. All right. While the velocity at every point is tangent. Inertia is trying to make the object go in a straight line. So the velocities are tangent, but the centrifugal force and the centrifugal acceleration are to the center. Now the centrifugal acceleration is always going to be v squared over r. We always assume it's moving with some constant speed in a circle. And r is, of course, just the distance from the center out to the edge. All right. Now, because this is an acceleration, the force, centripetal force, is equal to m, the mass, whatever is being spun in a circle, times ac. Now you can, of course, also write this as m v squared over r. Now, the trick is whatever is causing the object to move in a circle has got to equal the centripetal force. So if I have a mass, not writing on a string, I don't know what's wrong with this. Okay, then that tension has got to equal Fc. If I have a car on a curve, URVE, then the friction has got to equal Fc. Now quickly, you remember friction is mu Fn. This has to equal the centripetal acceleration, the centripetal force. Now you remember Fn is going to equal mg, or the weight, for our problems. So you kind of have to remember this. The other thing that equals centripetal force on our problems is force due to gravity. Now this is when you are usually talking about planets or orbits. All right. Then we have F of big G is equal to Fc. And you remember F big G is G, mass of whatever's orbiting, mass of the planet divided by the radius to the planet squared. And this is equal to Fc. Remember in all of these, this is mv squared over r. Now you see in all of these cases, except the tension one, look what happened to this mass. It's going to wind up canceling out, isn't it? But we'll deal with that when we go to problems. Let's try a couple problems. Okay, what is the acceleration? So we're looking for AC of a piece of dust on an old-fashioned record album. Okay, so it's a record album that's 15 centimeters. So R is 15 centimeters. Let's go on and convert that to meters. 0.15 meters. If the record is spinning at 33.3 RPMs. Oh man, we're trying to get you. The speed is 33.3 revolutions per minute. Okay, let's do a quick conversion here. 1 minute is 60 seconds. Let's see, 1 revolution is 2 pi. And how far is it going to go? What is R? R in this case is 0.15 meters. Let's see if my units are right. Cross these out in red. Revolutions cancels, minutes cancel. I'm left with seconds and meters. So I should be in pretty good shape. If I multiply this straight through, okay, let's go on and do this. Let's see, multiply straight across. So 33.3 times 2 times pi times 0.15 is 31.38 meters divided by 60 seconds, because 1 times 60. All right, so this becomes 0.52 3 meters per second. All right, now I want the centripetal acceleration, and this is v squared over r. So I've got my given, my unknown. Here's my equation. Now I'm going to plug in. So this is 0.523 meters per second, and I've got to square that, divided by r, and r in this case is 0.15 meters. And if I multiply this out, 0.523 squared divided by 0.15, I get 5.47 meters per second squared. Now, what's the tension in a rope? Let's see, it's 0.5 meters. Okay, that tells me the rope is 0.5, so that's R, which carries a rock of mass 2.50 kilograms in a horizontal circle with a velocity of 3 meters per second. So V is 3.00 meters per second. All right, now I want the tension. So if I've got a rock moving around in a circle, the tension is what's pulling it to the circle, to the center. So the tension is equal to Fc. So the tension has got to be mv squared divided by r. All right, this one's pretty straightforward. I plug in the mass is 2.5 kilograms. The velocity is 3 meters per second, and that whole thing is squared. And this is going to be divided by a radius of 0.5 meters. If I multiply this out, I get 45 newtons. Now determine the minimum coefficient of friction. Okay, so we're looking for mu. Required to keep, let's see, a car of mass 920 kilograms on a turn with a radius r of 26.8 meters if the car is traveling with a speed of 29.9 meters per second and the roadway is level. All right, so basically what this means is the car is going around, friction is going to the center, and so is the centripetal acceleration. So this is one of those cases where friction is equal to Fc. Now make sure you write that relationship down. That's very important. Okay, so what's friction? Friction is mu Fn has got to equal Fc as mv squared divided by r. Now let's see. Fn is mg, and this is mv squared over r. Now this is very interesting. Look what happens to my masses. And by the way, this always happens. My masses always cancel. So mu is v squared over rg. Let me plug my numbers in. D is 29.9 meters per second, and this whole thing is squared, divided by r, which is 26.8 meters, times g, which is 9.8 meters per second squared. Now I can tell you we have a problem right now. All right, 29.9 squared divided by 26.8 divided by 9.8 is 3.4. Goodness, this is much greater than 1. So we're talking Velcro. This is not good. Now, what speed in miles per hour must you drive your car across the crest of a hill of radius, let's see, r is 37.1 meters, in order to feel weightless? Okay. Now, let's look what happens when you're at the top of a hill. You have Fg going down, you have Fn going up. Now, you feel weightless. I'm going to write this down. You are weightless when your Fn is 0. Think about it. All right, let's see. My AC is going down. So let's see. I have Fn minus Fg is equal to m. Let me just write this as AC. All right, so I want normal force to be 0. Let's see. AC is going down, so I need a negative sign there. My negative signs are going to cancel. Don't worry too much about this. So FG is mg is m, and AC is v squared divided by r. So I just plugged this in. My masses are going to go away. Let's see, I want to multiply both sides through by r. So v squared is rg. So v is the square root of rg. Well, that's simple. So v is the square root. R is 37.1 meters. And g is 9.8 meters per second squared. So let's see what we get when we take the square root of 37.1 times 9.8, close your parentheses. You're going to get 19.07 meters per second. But that's not what we asked for. We asked for the speed in miles per hour. So let me convert it. 19.07 meters per second. And they tell me 1 meter per second is equal to 2.24 miles per hour. So take 19.06 and multiply by 2.24, and I get 42.7 miles per hour. Now think about this. That's not very fast. So does this make sense why sometimes when you're on country roads that are really bumpy and hilly, you can feel kind of funny? That's that weightless feeling. All right, what is the reading on a bathroom scale of a man of mass, 72 kilograms? He stands on it while riding in an elevator that's accelerating up 5.4 meters per second squared. Okay, this is not a circular motion problem, but that's okay. We'll do it anyway. All right. We have FG going down. We have FN. Remember, this is your bathroom scale reading, okay? And he's accelerating up at 5.4 meters per second squared. So I have FN minus FG equals MA. So the normal force, or the bathroom scale reading, is going to be FG plus MA. Let's see. FG is MG plus MA. Let me show you a trick. That might help you out a little bit. Let's factor out this M. This is M is G plus A. Remember we did this when we did forces. So this is 72 kilograms times G is 9.8 meters per second squared plus 5.4 meters per second squared. And so 9.8, remember to do this first. 9.8 plus 5.4 is 15.2. So this is going to be 72 kilograms times 15.2 meters per second squared. So I get the normal force, what the scale reads, is 1094.4 newtons. All right. Use the following information to determine the orbital velocity at treetop level on the surface of the moon. Oh, great. Okay. Let's see. The mass of the moon is 7.36 times 10 to the 22nd kilograms. And the radius of the moon is 1.74 times 10 to the 6th meters. Now you see if I add this plus 2 meters, all right, it's still going to be 1.74 times 10 to the 6th meters. It's not statistically significant. All right, let's see. This is one of those where, okay, now you just sort of have to pardon my picture. Here's my moon. Here's you. Okay, and we're going to assume he's standing at the top of a tree. All right, this is R. Now, what is causing the centripetal force here? Well, it's F big G. Has to equal FC. All right, what is F big G? F big G is G, the mass of the person, times the mass of the moon, divided by the radius of the moon squared. And this has to equal FC. Well, what is rotating around? Well, it's the person that's rotating. So this is going to be the mass of the person times the velocity of the person squared divided by the radius of the moon. Now watch what happens. The mass of the person or the tree or whatever is always going to cancel. And one of the radii will cancel with that radius altogether. So the velocity of the person squared is big G, mass of the moon, divided by the radius of the moon. So let's just square root both of these. So the velocity on the surface of the moon, basically, is the square root of 6.67 times 10 to the negative 11. The mass of the moon is 7.36 times 10 to the 22nd kilograms, divided by the radius of the moon, which is 1.74 times 10 to the 6th meters. And I get 1,679.7 meters per second. You'd have no idea you're actually moving that fast if you were standing there, but you really are moving pretty quickly. All right, now what is the period of rotation of Venus in Earth years if its distance of 1.08 times 10 to the 11th meters from the sun? And the Earth to sun distance is 1.5 times 10 to the negative 11 times 10 to the positive 11 meters. Okay, there are two ways to do this, easy way and hard way. Let me show you the mathematical trick way. All right, we know Fc has got to equal Fg, the centripetal force from Venus. So I'm going to put Venus. Venus is going around the sun. All right, this is the radius to the sun. All right, let's see. So what's rotating? Venus is rotating. So this is going to be the mass of Venus, V squared divided by R. And R is the radius of Venus to the sun, has got to equal big G, the mass of Venus, times the mass of the sun divided by the radius of Venus to the sun squared. Now let's see what cancels. The mass of Venus is going to cancel. One of the radiuses of Venus is going to cancel. So we're left with the velocity of Venus around the sun. Let me leave this squared. Is big G times the mass of the sun divided by the radius of Venus. Now, do you see it doesn't matter whether this is Venus or the Earth? Well, quickly, let's do this. Velocity, you remember, is 2 pi r divided by the period, because we want the period. So you know we're going to have to do this. So let me put this in here. So this is 2 pi, the radius of Venus to the sun, divided by the period of Venus squared has got to equal G, mass of the sun, divided by the radius of Venus. Oh, goodness gracious, let me multiply this out. 4 pi squared, radius of Venus squared, divided by the period of Venus squared is equal to G, mass of the sun, radius of Venus. Let me solve this for the period of Venus squared. Cross multiply. The period of Venus squared has got to equal 4 pi squared, the radius of Venus. Now I'm going to have 3 of these, divided by G times mass of the sun. Oh my goodness gracious. Now, what did we ask? I don't have the mass. I mean, I can find the mass of the sun. I can find this exactly. But they wanted it in terms of Earth years. So let me divide this by the period of the Earth squared. And you'll see, what is that going to be? That's going to be 4 pi squared, the radius of the Earth to the sun cubed, divided by G, mass of the sun. Now this is a mathematical trick we use sometimes to make our lives easier. The 4's will cancel, the pi squares will cancel. G and mass of sun will cancel. So this really, well, looks like it's harder. It's really not. The period of Venus squared divided by the period of the Earth squared is equal to, what are we left with? We're just left with the radius to Venus squared cubed divided by the radius of the Earth to the Earth cubed. Oh my goodness, that's pretty straightforward. So the period of Venus squared is going to be divided by the period of the Earth squared is going to be the radius to Venus, or 1.08 times 10 to the 11th meters cubed, divided by, let's see, the Earth's sun distance is 1.5 times 10 to the 11th cubed. Now you see the beauty here is these are going to cancel. All right, so 1.08 divided by 1.5 is what? This is 0.72 cubed. So the period of Venus squared divided by the period of the Earth squared is equal to 0.373 248. So let me square root both sides. And I get the period of Venus is going to equal the period of the Earth times about 0.6109. So the period of Venus is about 0.61 the period of the Earth. We could have gone through and actually found the period and converted it from years. But this is just sort of slick, don't you think? All right, now which of the following statements are true of an object moving in a circle at a constant speed? All right, let's see. The object experiences force which has a component directly parallel to the direction of motion. Well, no. The motion is in a circle, so the force is always to the center, and the motion is also always perpendicular, so that's not true. Inertia causes the object to move in a circle. No, inertia makes it want to go off. Inertia makes it want to go in a straight line. There can be a force pushing outwards on the object as long as the net force is inward. Well, yeah, of course. It's okay as long as the net force is inward. That one's true. Because the speed is constant, the acceleration is 0. No, that's not true. Let's think about this. AC is v squared divided by r. The speed may be constant, but you still have an acceleration. The acceleration and net force are perpendicular to each other. No. The net force is to the center, so is the centrifugal acceleration. Not true. If the net force acting on the object is suddenly reduced to 0, then the object would suddenly depart and travel tangent. Remember, tangent means straight off, and that is true. That is actually what happens. Imagine I swung a bobber around and it snapped off. It would fly into the classroom. That's true. The acceleration of the object is directly tangent to the circle. No. The acceleration is always to the center of the circle. A physics teacher, like me, ties an eraser to the end of a string and whirls it in a counterclockwise circle. If the teacher lets go of the string, and then the eraser hits a student or several students in the classroom. If the string is let go when it's at X, so it's right here, which students will get hit? All right, let's see. If it spins around, it's going to go off tangent. So it's going to hit JG first, and then if he ducks, it'll hit AF.